Okay, so last time we talked about the stability of benzene, and we said that alkenes like cyclohexene will do addition reactions like that with Br2. Benzene won't, even if you heat it up. I mean, at a certain point it will, but... and then if you compare the energies of cyclohexene and benzene, you'll see that even for three of the type of double bond that's in cyclohexene, you would expect it to give off 360 kilojoules of energy during a hydrogenation like this, but it's actually only 208. So benzene is a lot lower in energy than you would expect based on just the double bonds. Okay, so to explain this, we have to look at a little bit more molecular orbital theory. And so one of kind of the basic parts of MO theory is that you can take two atomic orbitals and combine them to form two molecular orbitals. So one way we can do that, molecule. I really can't write the word molecule today. So if we've got two atoms that are going to come together to form like a diatomic molecule or something, we've got some atomic orbitals. And we'll say for today's purposes that we've got one electron in each of the atomic orbitals. When they come together to form a molecule, we're also going to get two molecular orbitals. One of them is going to be higher in energy, and one of them is going to be lower in energy. And these two electrons are still going to be there in the molecular orbitals, but they're going to be in the lowest possible energy state that they can, which is going to be in that lower orbital together. And so this orbital down here, we call that the bonding orbital, because the electrons that make the bond are in the bonding orbital. And of course that's lower in energy, so we can make an axis here for energy. And then up here we've got the antibonding orbital. If you have electrons that are in that antibonding orbital, then they weaken the bond because they're really high in energy, and that's not favorable. That's higher in energy. Have we seen at least something like this before? Probably a little bit. Okay. So we know benzene is flat or planar. And it's a ring. We've got all of those orbitals on the same plane as each other. It can kind of act like one giant molecular bond, I guess is one way you could put it. But really what's happening is six atomic orbitals. So if we sort of extend this and we have 6 atoms, and from those atomic orbitals we get 6 molecular orbitals, 1 from each carbon atom. But the important thing here is when we go and make those 6 molecular orbitals, of those we have 3 bonding and 3 antibonding. The bonding ones are super low in energy because they end up getting pushed further down because there's so many atoms. And to counteract that, the antibonding orbitals are extremely high in energy. Fortunately, all the electrons go into the bonding orbitals, and that makes the bonding orbitals, the electrons in the bonding orbitals, extra stable. So another sort of way to look at this is like this. I think this is going to work out. Okay. All right. So there's our benzene ring. It's kind of ugly, but okay, there we go. So there's our orbitals on the benzene ring, and in the case where these are all in the same phase, which is going to be one of those low energy bonding configurations, we have overlap all the way around these top lobes that are colored in, and we've got overlap all between the bottom ones that are white. And so you get a little molecular orbital hamburger, and we have tons of space on the top bun and on the bottom bun for electrons to slide around. And that, sort of that increased number of options for the electrons to go wherever they please gives us really low energy for benzene and for other aromatic compounds. Okay. We've talked about benzene, but there's other aromatic compounds, and so we're going to discuss those and how to identify them. So, there's 4 criteria that compounds have to satisfy in order to be aromatic. The first is they've got to be a ring or rings. Okay, benzene checks that one. Good. The second is they've got to be flat, planar. This one is a little harder to tell sometimes. And unless I specify that something is not planar with wedges and dashes or with like a 3D drawing kind of thing, you can assume that anything that's drawn kind of flat on the page is going to be planar. The third thing is we've got to have that conjugated pi system. And then the fourth, which is kind of the tricky one, is it has to obey Huckel's rule. It's really more like Huckel, but it has to obey Huckel's rule. Huckel's rule says that in order for something to be aromatic, it's got to have 4n plus 2 pi electrons, where n can be any integer or 0. It can be 0 as well. So some examples of that would be cyclobutadiene. So this has 4 pi electrons, right? Because it's got 2 pi bonds, 4 pi electrons. That is not 4n plus 2. That's just 4n. And so that fails Huckel's rule. Okay, we know benzene is aromatic, so it's got to pass, but let's make sure. So benzene has 3 pi bonds, which is 6 pi electrons. 6 is 4n plus 2, n equals 1. And so that passes Huckel's rule. Okay, let's expand and give it one more pi bond. Sorry, there we go. Cyclooctatetraene. Just an 8-membered ring with alternating single and double bonds. How many pi electrons does this have? Yeah, so it's got 8. And does that pass or fail Huckel's rule? 4n plus 2, you can't make 8 out of that. So that's a fail.
So how would something better than benzene?
So you've got to have, okay, so 4n plus 2 can equal, if n equals 0, then that's 2. We could have 6. We can have 10, 14, and just increasing by 4 pi electrons each time. So we use our favorite naphthalene. That has how many pi electrons? Yeah, 10. And so 10 is 4n plus 2. So that works. Yes?
Can aromatic compounds ever just have 2 pi electrons?
Yes.
Would it not be conjugated pi system then?
It still would be conjugated, but you really the only good example of that is that. Because it's conjugated, because we can, there's conjugation between these 3 carbons. We can draw resonance structures there. It's only got 2 electrons. And so that's actually aromatic, as cursed as it looks. Okay, so based on these criteria, it's aromatic if it passes rules 1 through 4. Okay? It's non-aromatic if, and you would assume if it fails any of the rules that it would be non-aromatic, right? No, it's actually non-aromatic if it fails any of 1 through 3. But if it fails only Huckel's rule, then it's anti-aromatic. Okay, so look through these on your own and see if you can classify these as aromatic, non-aromatic, or anti-aromatic. He's just off. Okay, the first compound, what is that? Yeah, anti-aromatic. So if we look at our rules, it is a ring. It is planar. It's got a conjugated pi system, but it fails Huckel's rule. Second one. Yeah. So that's not a ring. And at that point, it kind of doesn't matter, you know? It's not necessarily planar. It does have a conjugated pi system, and it does obey Huckel's rule, but it doesn't matter if it's not a ring. Third one. Yeah, non-aromatic. So this one is a ring. It isn't planar because it's got sp3 carbons. More importantly, it doesn't have a conjugated pi system, and it also doesn't happen to obey Huckel's rule. And the last one, anthracene. Yep. It's made of rings, it's flat, it's got a conjugated pi system, and it's got 2, 4, 6, 8, 10, 12, 14 pi electrons. How's that? Questions? Yes?
So, if it fails one of the three, but it also fails then it's just still considered non-aromatic?
Right. Yep. Yeah, so as soon as it fails 1, 2, or 3, it's non-aromatic, regardless of Huckel's rule. Okay, so let's look at some more sort of specific examples. It's a class of compounds called annulenes. And these are just rings that are entirely made of one conjugated pi system. So, I think we know a ring that is made of one big pi system. That's this compound, which is called, you guessed it, 6-annuline. But nobody actually calls it that, it's just benzene. So we can sort of use that notation to go further. I'm going to skip one that's interesting. There's, no, this guy. I think I drew them correctly. This is 14-annuline. So benzene is aromatic. 14-annuline is also aromatic. And then there's one in the middle here. This one, which looks like naphthalene, but it's not quite. This is 10-annuline. And you would think that it would be aromatic. The problem is there's a hydrogen here, and there's a hydrogen there. And those crash into each other. And because of that, it actually forces the ring out of planarity. So it's not planar, and because of that, does It's actually not aromatic. So we don't really run into these very often, but they're good to know about. And this tin aniline is a good example of something that satisfies all of the rules for aromaticity except it's non-planar only because of those stupid hydrogens in the way. Naphthalene doesn't have that problem because it's got a bond there and no hydrogens. So on the last page, I showed you that this cursed where is this? This cursed ion here. We can have ions that are aromatic. That's fair game. A really good example is you start from cyclopentadiene. You probably recognize this from Diels-Alder. This is a really good Diels-Alder diene. If we deprotonate cyclopentadiene, we get that. This is the cyclopentadienyl anion, or we just call it CP. I'm partial to this because this is what my PhD research was on. And you'll notice that our starting material here is non-aromatic. It's not conjugated. Well, it is conjugated, but the whole ring isn't conjugated. However, this is aromatic. Because we can draw resonance structures where we send that negative charge all around the ring. We've got 6 pi electrons, 4 from the double bonds, and then those electrons, that lone pair on that carbon, is delocalized because we can move it around the ring. Yeah, Maddie?
You mentioned the question.
Okay. Yeah, these are pi electrons because they're able to move using those resonance structures around the ring. So there's an anion. We've also got the seven-membered ring. This is non-aromatic for the same reason. We've got 2 hydrogens here. But if we abstract H minus from this, we end up with that. Got a positive charge there. This is called tropylium. Not exactly sure where that name comes from, but I like it. And this is aromatic because we've got those 6 pi electrons, and how is it conjugated? Well, we can draw resonance structures where we push electrons toward that positively charged carbon, and so that positive charge can move around the ring. So those are both used as good ligands in organometallic chemistry. We won't talk about that very much until the end, but just some useful aromatic ions there. Probably more important are heterocyclic compounds that are aromatic. And so A heterocycle or a heterocyclic compound is one where we have a ring and then some sort of heteroatom like oxygen, nitrogen, sulfur, etc. So one we'll see a lot of is this. So it looks like benzene, it's just got a nitrogen instead of one of the CH groups. That's pyridine. Stinky fish odor liquid of death. It's really unpleasant. But it's an important molecule. That's pyridine. Five-membered ring with nitrogen with a hydrogen. That's pyrrole. We're going to talk about the difference between these. They're both aromatic, but the lone pair ends up being kind of important. And then sort of a smattering of other ones. Five-membered ring with oxygen, that's furan. And you got sulfur, thiophene. And then there are also some interesting ones. This one is pretty important biologically. That's indole. And then just for fun, if you take these five-membered rings and you put an arsenic atom in it, we're never going to use something like that. But that's called arsol. Okay, so the ones that we're going to talk about today are pyridine and pyrrole, but just be aware that there's sort of a range of a lot of different looking type of aromatic compounds that you'll see. So, in pyridine, the lone pair does not participate in aromaticity. So we say that it's localized because it's sort of staying in one spot. And we can prove that to ourselves by drawing a resonance structure of pyridine like we do with benzene, where we just scoot each of the pi bonds around in the ring. And so we get this one. And as you can see, the lone pair just sits there. It doesn't move in the resonance structure, and so it's not involved in the aromaticity. It's not one of those 6 pi electrons. If they did count as pi electrons, right, this would have 8 and it wouldn't be aromatic, but fortunately that's not the case. Another reason that we know that the lone pair is not involved is that nitrogen is basic, and so it will collect a proton from a lot of different bases to make pyridinium, but anyway. So let's contrast that with pyrrole. So here, the lone pair does participate in aromaticity. So we can draw something like this. Now, this certainly doesn't look as pretty as the resonance structure for pyridine or for benzene, but it is valid. And we'll see that here. Okay, so we've got our hydrogen. We've got a double bond here now. There's now a double bond here, and then we've got a lone pair on that carbon. So we've got a negative charge there, and then this nitrogen has a positive charge. We can actually keep going here and do that, have that go there, and then have our lone pair come and make a bond. There. What did I just do? Did something weird. What did I write? This is not correct. Oh, ha ha ha, lol. Well, crap. Now that means I have to redraw the whole molecule because I messed it up with mechanism arrows. Okay, let's do this again. There we go. Okay. That's what I was looking for. Okay. Sorry. Okay, but anyway, the point that I'm getting at here is that this lone pair has to move into the ring and start, doing all this resonance structure and stuff in order to be able to draw these resonance structures. And additionally, right, we've got 1, 2, 3, 4 pi electrons in those pi bonds, and then the lone pair gives us the other 2 that we need for a total of 6. So both have 6 pi electrons. And then in the same way that pyridine is basic at the nitrogen atom because that lone pair is free to react with other things, pyrrole is not basic at the nitrogen atom, so it's not going to pick up a proton or anything like that. Okay. One of the shortcuts for figuring out if lone pairs like that are involved in aromaticity is to look at the single and double bonds on the atom that the lone pair is on. So in pyridine, the nitrogen has a double bond, so it's already kind of got pi electrons associated with it because they're in that pi bond. And so that's generally an indicator that that lone pair isn't going to be involved in the aromaticity. But in pyrrole, that's not the case. We've got only single bonds to that nitrogen. And so that lone pair is going to be involved. So, okay, so in this one, what lone pairs are involved in aromaticity? In other words, localized versus delocalized? Well, the first place to look is that amine there. It is outside the ring, and so there's no possible way that those electrons in the lone pair can be aromatic, because one of the requirements for aromaticity is that you've got to have a ring, and the electrons have to be in that ring. So those are, that's a no for that one. What about the this nitrogen? Well, it's in the ring, so that's okay. But we've got a pi bond already to that nitrogen, and so that means that, like in pyridine, those electrons on the nitrogen are not going to participate. However, we can draw a resonance structure where some of our electrons on the sulfur can come down. If we wanted, say, we could move this pi bond over here, and then that pi bond up onto the carbon atom. So that gives us this. Where, okay, so our lone pair on the nitrogen hasn't done anything. This lone pair was initially a pi bond. The amine is not affected, and then we've had one lone pair on the sulfur start to participate. So here, one of our lone pairs on the sulfur can participate in aromaticity, but that's it. The same would go for oxygen. in a molecule like furan. Only one of those lone pairs is delocalized. Yes.
Why would the 5 bond not be formed between the sulfur and the negative charge of the cation?
You mean like right here? Why wouldn't we? Yeah, that would break sulfur's octet. It would give it 10 electrons, which sulfur is a third row element, so you technically could do that. But that would be a low contribute, a resonance structure with less contribution to how the structure actually behaves. So not necessarily illegal. Cool. So make sure you turn in your homework. And next time we'll talk about reactions of aromatic compounds.